Hello, everybody. I'm Chen Mingzhang from Geotechnical Engineering Center at University of Queensland, Brisbane, Australia. I'm going to talk about the progress of instrumented column test to assess oxidation and leachate. So this test is conducted in Western Tasmania, Australia, where the average rainfall is around 2 meters. It's not only the instrumentation monitoring result, but also the numerical result that will be discussed. So the background of the study is that the acid rock drainage containing potential acid generating waste rocks pose serious risk to the receiving environment because it could have high pH or low pH or rich chemicals. The ARD is predominantly due to two processes. One is the oxidation of the pyrite when the pyrite meet with oxygen, and then is the transport of the oxidation products through rainfall infiltration. Clay are always considered to be the best cover because their air permeability and also hydraulic conductivities are very low to retard the above mentioned process. But in many sites, clay is not available. And also cover are being done at the end of the dumping activity. During the activities, the oxidation cannot be minimized. However, it is very common that at the site, non-acid generating wastes and acid neutralization wastes are available. So it is possible that once the cold disposal is being could potentially reduce the pH of the leachate as well as minimize the acid rock drainage process. For that purpose, we set up 6 large columns to investigate the effectiveness of various covering comprising no acid generating or acid neutralization waste in inhibiting ARD. So in terms of the 3 types of waste available on site, there are 3. There are A-type wastes and B-type wastes. Both of them are considered as no acid generating. We also have got the D-type waste that is potential acid generating. So if we look at the material paved in a square meter board, we can see that the waste is a mixture of large rocks plus a sandy or COT soil. We did the soil water characteristic for the fine part and then realized that the soil-like material behaves somehow like a sand and silt because the volumetric water content decreases very quickly as the suction increases. Below is the mineralogy testing using XRD analysis, and this is one of the samples. Later on the samples we conducted realized that there is bit variations about the mineralogy of the mineralogy compositions of the material. But nevertheless, we can see that the quartz mica is relatively stable. Chlorite, calcite, dolomite, albite is related to the hydrolysis process, which could potentially neutralize the pH. There is a bit pyrite in D-type and slightly amount of pyrite in the A-type, but that will not change the pH as the analysis will later on show. We will discuss that later on once we do the numerical analysis. In the setup of the column is shown in the graph here. So the column is 4 meter high and 1 meter in diameter. The top of the column is open to the atmosphere, where the bottom of the column has got the drainage through a U-bend that will allow the water coming out from the column but prevent the air coming from the bottom. We've got the leachate connector to connect the sample for the component for the chemistry analysis, and after that it will go through a tipping bucket flow meter to work out the total amount of outlet from the bottom of the column. So the waste rocks will be allocated inside the column, and the instruments stretches from the bottom of the column all the way up to the top, and then following a cable tray connected to a data logger. So the data logger will automatically transmitting all the data to the web cloud for visualization. So in total, we have 8 oxygen sensors, 8 moisture sensors, and 8 suction sensors deployed for each column. So the allocation of the wastes is done by the following ways. The column 1, 2, 3 are considered as control with relatively homogeneous A, B, D type. They are loosely placed, coarse-grained. And the column 4 is A type compacted on top of D type waste. The column 5 has got the B type waste on top of the D type waste. The number 6 is evenly ratioed, loosely placed, well mixed of 3 types of the wastes. So we, as mentioned, that the columns are instrumented heavily. So at the Geotechnical Engineering Center, we are developing in-house instruments. Some of the instruments are commercially available. Some of them I designed by ourselves. So the instrument that we deployed includes the electrical moisture sensor, temperature suction sensor, thermal suction sensor, oxygen concentration sensor. This is the sensor that is relatively unique because it measures the oxygen concentration of the soil using optical method, which is much better than the galvanic ones where it suffers from zero shifting. We also designed a tipping bucket based flow meter. So here is the outlet of the bottom of the column, where's the U-bend, and then leachate connector. And once the water comes out of it, the tipping bucket is able to capture every single droplet coming out from the column, which is much more accurate as compared to the propeller-based flow meter. So all the instruments, it's quite a large number, are connected to 6 in-house made data logger. So those data loggers will send the data to the web cloud for analysis in real time. So even now, it's been there for 3 years and still we are receiving data from the local environment. So the construction is done by firstly level the ground using gravels, and then putting the bottom allocations, the bottom column on top of the gravel, and here is the opening at the bottom opening, and the internal is connected to the agar pipe to enhance the outflow. We use the geofabric to enhance the bottom permeability, and the wastes are then being dumped inside with the instrumentation. So here is the cable. And once it's been filled, we put all the strings on top of the waste and then using the rubbers to seal the joints between the sections. And then another section comes on top of that. So we repeat that process until the column reaches 4 meters designed height. So here are the results. The temperature fluctuation of the 6 columns are shown on the screen. So there are clearly 2 types of fluctuations. So one fluctuation is the daily fluctuation, that is averagely 15 degrees Celsius. The other fluctuation is the yearly fluctuation, where during the winter, which is June, the temperature is around 5 degrees Celsius, whereas during December, the top temperature is around 25 degrees Celsius. Remember that this is in Southern Hemisphere, so the summer is in December. From the temperature measurement, we cannot see any spikes, abnormal spikes of the temperature, which indicating that the oxidation process within the waste rocks does not cause any temperature rise locally. So this is not identified. So if we look at the change of moisture over time, so let's first look at the videos over time. We can see that over 1 year, the top surface has settled quite a bit. and the settlement is particularly high for the rest of the column except for the A-type column. It's quite significant, and it's still going down. So here this graph shows the potential evaporation rate, which is directly correlated to the season. So during summer, it's around 8 millimeters per day, where during winter, it's around 2.5 millimeters per day. And the rainfall, as mentioned below, 2 meters per year. And the moisture condition, it all shows three interesting patterns. So at the very beginning, the moisture content is relatively low because the waste are dumped with dry condition. And over time, the wetting front start off percolating from the top to the bottom. And later on, they will pretty much reach a stable condition. And that is very consistent across all the columns. And during the stabilized process, we also see that it is possible that some of the locations would have a slightly decrease of moisture content. And that is actually because of the gravity drainage, because we could imagine that the flow is not actually 1D within those columns. So there are somehow like a wetting front, and later on the wetting front, which is basically the preferential path, and later on the preferential path will expand. That will allow the top flow quicker as compared to before, which could help drain out the local moisture down to the bottom, which is the reason why we could have a sudden decrease of the moisture content. And below are the moisture profile over time, profile over depth. So we will discuss that from the next slide. So here again is the moisture profile over depth. What we learned from this is that over 2 years of monitoring period, the moisture content pretty much reached a kind of equilibrium, a steady state condition, because it doesn't change much over time. But if we look at the steady state condition, what we can see is that at the bottom section of the column, the hydrostatic pressure has already established where the bottom is close to saturation, whereas 2.5 meters above the surface, it is relatively low. Another interesting phenomenon is that the moisture is not increasing monotonically over the depth of the column as we thought. Instead, it is fluctuating quite a bit. So sometimes a moisture sensor would be higher as compared to the bottom one. And even for the top, for the D-type, column 3, column 5, and column 6, we could potentially have moisture hold up on the surface. This is probably induced by, first of all, the settlement of the column, as we see from the pictures. Also, there is a bit possibility that the combination of A plus B plus D type would somehow cementing the surface. And once the surface is being cemented, the capillary process has been enhanced. So at the same suction, the moisture content will otherwise higher. So let's look at the oxygen concentration over time. So again, you can see how the top is settled over time. It's very, very evident from the videos. What we can also see is that during the rainfall seasons, when the rainfall becomes intensity, we can see that the oxygen start of decrease. But such decrease is not dropping the oxygen concentration down to zero. However, once the rain has somehow stopped, the oxygen started to come back of it. And then again, if there's a rainfall, the oxygen concentration starts dropping down and later on coming back. So roughly, it does not reduce down to zero. So the conclusion is that if we use the core waste, acid rock core disposal, we are not able to completely minimize the oxygen ingress to the soil. However, if the top moisture content is relatively high, the oxygen ingress could be somehow minimized. So besides the field monitoring, we also have the numerical models in parallel to that. So TOUGH-REACT was used to simulate the transport of water, solute, gas, oxygen, and associated kinetic chemical reactions in the column. So the top of the column is prescribed as a atmospheric boundary with 21% of oxygen concentration. The bottom of the column has got zero capillary pressure because of the free drainage boundary and also our oxygen concentration of zero. Rainfall and gas ingress is allowed from the top of the column. The bottom column will allow the leachate outflow with the chemicals. So here is all the reactions considered within the column. The XRD data were used to configure the waste compositions. Kinetic reactions between solute and minerals are included. So below are the list of reactions considered. So pyrite is basically the oxidation process. The dolomite, calcite, and gypsum and chloride and talc are basically the hydrolysis process, which could potentially neutralize the drainage and the siderite also. Heat transport is neglected because we didn't really see a significant increase of temperature induced by the oxidation process. And the model was verified by comparing the monitored moisture profile and leachate outflow rates, chemical compositions, with the simulated result. And the model will later on be used to estimate the water quantity over the next few years. So here is the comparison of moisture and moisture profile over depth for the 6 of the columns. So the purple one is the steady state moisture profiles, and the red ones are the simulated result. So in general, the model captures reasonably well about the increase of the moisture content over the depth, but it does not consider the fluctuation of the moisture over the depth because the column is considered as a 1D process. It is reasonably well captured the hydrostatic pressure at the very bottom of the column. And in terms of the moisture holdup, we configured the top section of the column 6 as a silt-like soil with different soil water retention parameter. And by doing that, we are able to simulate the moisture uphold at the top section of the column. So below is the moisture, the simulated and monitored outflow from the bottom of the column. So the top 2 graphs are the rainfall over time. And again, the red is the simulated result, and then purple is the measured. So unfortunately, that column 1 and 6 has got a bit technical issues because the joints were leaked before it meets with the tipping bucket, which is the reason why it's not the measured result does not change clearly. However, if we look at the rest of the 6 of the column, the simulated result captured relatively well the changes in the outflow from the bottom of the column, and the intensity at the phase is relatively well captured, which is again an indication that the flow are well simulated within those columns. And then let's look at the chemistries of the leachate and the outflow. So for the column 1 and column 2, which is shown in purple and red, the pH is roughly around. So the pH for all of the columns has got a trend where it increases slightly and later on decreases. But this is not the case for the column 1 because column 1 does not have significant amount of pyrite. So the simulated result for column 6 well captured the increase of the pH over time and later on drop of it. And even after 6 years, the pH is expected to 9. But of course, this needs to be calibrated against the leachate analysis over time. And also the top the hydrolysis process, the neutralization process, is slightly overestimated. The sulfate concentration for the column 1 and 2 is relatively low. However, for the rest of the column where D-type is available, the sulfate concentration is very high, and also it decreases almost monotonically over time. So the simulated result also captures relatively well about the sulfate distribution over time, and it's expected that after the year 6, it will reduce down to 0. The iron concentrations shows a bit interesting result as well as compared to the sulfate. Remember that if it's pyrite oxidation, the amount of sulfate and iron needs to be proportional, but this is not the case because the iron concentration are relatively lower as compared to the sulfate concentration, which is probably induced by the iron precipitation within the column, which we'll discuss later on. And the calcium precipitation, the concentration, is again very low from the column 1 and 2, but for the rest of the column where D-type exists, it was relatively stable during the first 2 years and suddenly decreases. And this is also captured by the model. And finally, the magnesium concentration, it shows similar pattern as compared to the sulfate, where the model captures relatively well. And again, after 6 years, the concentrations for all the irons start to wind down. So here is the mineral distribution within the column. So the 0 here indicates there is no precipitation or dissolution. So the negative goes to the dissolution and the positive goes to the precipitation. And what we can see is that the chloride and calcite for the column 6 is dissoluting over the whole depth of the column, whereas the gypsum and the siderite is precipitating at the bottom section of the column. And this is the reason why the iron is not coming out as a leachate, because it's been precipitated. And interestingly, once we connect the leachate, we can clearly see that some of the newly produced minerals floating on top of the leachate, and it's very brittle. So once we touch it, it starts off collapsing. And so the conclusion for the PowerPoint is that the moisture profile in the 6th column seems to be stable. A significant settlement occurred in the D column, where A, B, D wastes are mixed together, and due to the hydrolysis of chloride and calcite in particular. The settlement of the waste would help hold up the rainfall and also increase the evaporation and reduce the outflow of the leachate. The moisture hold up will also help in minimize the oxygen ingress and reduce the acid formation. Pyrite seems to be depleted in the column, which resulted in the increase of the pH as the hydrolysis process continued. That's the end of my presentation. Thank you.